Good morning, everybody. Today we will start our discussion on introduction to mathematical approaches to turbulent flows. Now, I have a full course on turbulent flows, and I have given the URL of that course. It's also available on NPTEL website and NPTEL site of IIT Kanpur, NPTEL site of IIT Madras, personal homepage. This is a full course. As you know, that turbulence is so vast that its salient features cannot be covered in one or two lectures. Rather, I would say theoretical foundation of turbulence that needs one full course. Mathematical approaches, modeling approaches that usually combine all the aspects and that need one full course. Obviously, experimental approaches and interpretation of results that need another full course. So, what we are trying to do here, trying to give you, some aspects and how to model turbulence flow in affordable computational initiatives or affordable computational framework. Now, characteristics, features of turbulence. First feature I would like to mention is irregularity. That is complex variations of velocity, temperature with space and time. And these are often called fluctuations. The irregular motion is generated due to random fluctuations. It is postulated that the fluctuations inherently come from disturbances such as roughness of the solid surface, and they may be either damped out due to viscous damping or may grow by drawing energy from the stream. At a Reynolds number less than critical, the kinetic energy of flow is not enough to sustain the random fluctuations against the viscous damping. And in such cases, laminar flow continues to exist. At somewhat higher Reynolds number than the critical Reynolds number, the kinetic energy of flow supports the growth of fluctuations and transition to turbulence is induced. So you get a sort of rudimentary idea about some characteristics, features of turbulence. Strong mixing. So basically high transfer rate of momentum, heat and mass by fluctuating turbulent motion is practically most important feature of turbulence. Turbulent motion is always 3D. Even for parallel flow, we have read parallel flows, like Plain-Paiseli flow, Hagen-Paiseli flow, some such flow where u, the flow direction velocity, is function of only cross normal direction, and time there for turbulent flow we can say it is a mean flow plus fluctuation. So y is the normal direction and capital gamma is a space variable. Even if the bulk motion is parallel, the fluctuation u prime being random varies in all directions. Now let us look at the continuity equation where del u del x, u is substituted by u mean plus u fluctuation. As we have written here, u equal to u mean plus u fluctuation. This is u instantaneous. So we have plugged in that and then we have gotten this equation. But in this equation, since u prime is present, so del u prime del x is not equal to 0, which demands that there is some v prime and there is some w prime. Even though mean velocity of v is 0, mean velocity of w is 0, but there is time mean velocity is 0, time mean velocity of v is 0, but at any instant there is fluctuation of v and w since fluctuation in u is present. And we will see later separately continuity equation has to be satisfied, or u is satisfied with fluctuating components. That means del u prime del x plus del v prime del y plus del w prime del z equal to 0. That is why for non-zero value of del u prime del x, del v prime del y and del w prime del z will exist. Turbulent motion carries vorticity. It is composed of eddies interacting with each other. So this is a turbulent jet, and you can see the velocities at different points are being sensed, and that signal is reproduced here, or the signal is traced here. So this is basically, you can see that at different positions the u velocity together with its fluctuations, how does it vary? This is variation of u at maybe this location, then u at this location, and then u at this location. How does it vary? With time. And at any instant of time, if you try to see, you will not be able to find any coherence between these instantaneous u's. So every instant it is changing, although there is a possibility to having a mean value which at every point probably will time mean value will be same. We'll come to this aspect again. So we can say from here wide spectrum of eddy sizes and corresponding fluctuation frequencies are present in a turbulent flow. Also, one can say the motion is not organized, it is chaotic, and it has random behavior. So random behavior means non-repeatability. Although a finer analysis of turbulence by sophisticated numerical and experimental tools. One can show presence of a coherent component in seemingly random turbulent motion. This is again, a very special topic and to be discussed separately. Many of you may be knowing the name coherent structure in turbulent flows. This was a discovery of a famous scientist, Professor Fazle Hussain, and this is even today a topic of research. Enhanced diffusion and dissipation, three-dimensionality and vertical structures, I've already mentioned about it, and intermittency in space and time. These are also random fluctuations in space and time. So these are characteristics feature, and from these whatever we have just discussed till now, it appears that it is impossible to apply any systematic computational tool to analyze turbulence. But scientists have put in effort. It is not so. It can be done. First, I will mention about a technique which is called direct numerical simulation or DNS. The exact equations of any flow situation are basically continuity equation and Navier-Stokes equations in three orthogonal directions. So, four equations and four unknowns, U, V, W, and P. Ideally, this can be solved without any problem, even for turbulent flows, and that is what is ideally direct numerical simulation. But what one would need, number one, discretization scheme should be absolutely error-free. Errors, like truncation error, diffusion error, artificial viscosity, dispersion error, all these errors should be tending to zero, almost zero. So these are special techniques, discretization techniques. Then also for we know that turbulent fluctuations can vary, or turbulent motion can vary over a wide scale. Its variation, fluctuations spatially in a domain may be, in the scale of meter in the flow direction, in the scale of centimeters in the cross flow direction. But there, the minimum level of fluctuations that given by time and length scale, these are expressed by Kolmogorov scale, can be fraction of a millimeter. So you can see, in order to simulate a domain directly without applying for high Reynolds number flows any turbulence model, you need a grid size which is able to capture the smallest scales of fluctuations. Now I will give you a very rudimentary example. This is just to give you an idea. I mean, this is not exactly the reason of not going for direct numerical simulation always, but why direct numerical simulation is difficult, this is one of the reasons I have tried to explain. See, maybe equate flow type of flow we are discussing. So this is the bottom plate, this is the top plate. Top plate velocity is u naught, obviously bottom plate velocity is 0. And this is the slope of velocity, so velocity is increasing and the domain is divided by number of grids. So velocity is increasing, delta u is the velocity increase from in the normal direction, across normal direction, perpendicular direction. And this is the grid size delta x. So delta x is the grid size, delta u is the velocity change, and n is the number of grid points per coordinate direction. Usually most of the affordable computers we can take for some flow simulation. If it is 3-dimension, it is considered to be a very powerful computer if we are able to take 100 by 100 by 100 grids. So that means 1 million grid points. Now one can easily show that if you take 1 million grid points, what would be the upper limit of the Reynolds number? Here we have done sort of very rudimentary calculation. Del u into del L, if this direction is L, small del x or del L, whatever you call it, del L by nu, we know the computational stable computational requirement should be less than equal to 2. So del u we can say is u naught by n, and del L or del x is basically L by n multiplied by 1 by nu viscosity less than equal to 2. So this makes u naught into L by nu is less than equal to 2n square, and n is 1000. So basically Reynolds number less than equal to 20,000. So if we take 100 by 100 by 100 grid, our Reynolds number based on characteristics dimension has to be less than 20,000. So there is a limitation for which direct numerical simulation for all the flows is not always possible. You will need very fine grid size, you will need very highly accurate discretization scheme, and also in the time direction you must be having huge data every small time interval to finally draw a conclusion about the flow grid. Now, but direct numerical simulation is a very vibrant area of research in turbulence. Then I will mention about another very exciting area of research in turbulence is large eddy simulation. Here, the grids can be larger than the direct numerical simulations. So, the fluctuations that are scale wise falling below the spatial scale defined by the grid size, those fluctuations can be handled by a model, and these are called subgrid scale models, and one can go for reasonably high Reynolds number flows. But there is yet another difficulty. When viscous sublayer is not resolved, because as you know, turbulent fluctuations, as one approaches the confining walls, because of the no slip boundary condition at the wall and the gradual damping of the fluctuating components very close to the wall, we call it viscous sublayer, where flow is like laminar flow. And since there is no fluctuation, so describing velocity and other turbulent flow related parameters within the viscous sublayer, those are to be very accurately determined, or one can also apply something called wall function. We will discuss about it little later. So that sublayer and the turbulent regime can be breached through some functions which are called wall functions. So with the help of wall functions, one can go for even slightly higher Reynolds numbers, but even then one needs reasonably high number of grids. So grid resolution, or the fineness of grid, the requirement is not as much as direct numerical simulation, but here also grid size has to be quite small. And usually for laminar flows, when you go for grid independence test and all, by reducing the grid size, increasing the grid numbers, for large eddy simulation techniques, definitely we need much larger grids than those type of grid requirements. It is not as high as I have already mentioned. It is not as high as the requirement of DNS, but here also grid requirement of number of grids is quite high. So with all these, for usually flows of engineering importance, where we want to calculate pressure drop or screen friction, or if it is heat transfer, finally the average Nusselt number or average heat transfer. For those requirements, we often cannot use LES or DNS. Maybe LES is being implemented for all complex flows, including combustion, where uncertainties are quite significant. But even now, it is not really used for all engineering flow calculations. For very special purpose flows, it is used. Maybe in another 5 years, it will be a method of calculating engineering flows. And here also, in order to derive the correct statistics, one required to progress in time. And maybe I have mentioned it here, that you can see that 100,000 time steps may be needed. Instantaneous flow fields may be needed. We need not store all 100,000, but there are ways of calculating from such instantaneous flow fields the time average flow, then a flow field, etc. So large number of time steps or time instants are needed to derive the correct statistics. So arising out of these difficulties, although DNS and LES both are very important and very elegant, scientifically very elegant methods, but for all engineering flow calculations, these are not really used in practice. So third method what we have suggested here is statistical calculation methods. Now, details of turbulent fluctuations usually not of interest to engineers for design purpose. Hence, statistical approach is taken and turbulence is averaged out. So we have shown 3 sample signals. Here you can see how the velocity is varying, and if we average it out, this is the U average signal. Here also we can see instantaneous velocities, and if we average out, we have found out U average. It is not a function of time at all. Here also again instantaneous signals versus time we can see. But if we average out, we can see the average velocity is a function of time. Here the time average velocity is not a function of time. Such flows are called stationary random. It is random, but time average value is constant, stationary. Here the random fluctuations are seen, but time average value is again function of time. But this time period is quite large and much greater than the time period of turbulent fluctuations. So turbulent fluctuations time period is so small that frequencies may be as high as several kilohertz. Time period is small, it is 1 by time period is the frequency, and frequency is of the order of maybe several thousand hertz. Here time period is large and the frequency may be several hertz, much smaller frequency than the turbulent frequencies. So time period is much bigger, much larger than the time period of turbulent fluctuations. So one can average out the signal over this time period. And here, if we take a large time and average it out, we will get average quantities. So instantaneous ui, that means it's a vector quantity representing uvw, equal to ui bar plus ui prime. Pressure is p bar plus p prime. Now average velocity is over a time period. This is what I was saying. Here a large time period can be taken. Here also you can take a large time period, but at least the time period should be greater than t2. So, and over during this time window, if we perform the integral divided by t, we'll get the average velocity. Now here again we have represented, this is the average velocity. These are all instantaneous values. So uj bar is the time average velocity and uj prime is turbulent velocity fluctuation in j direction. Turbulent flows can only be mentally digested if time average properties are given. These are denoted with a cross bar over the variable, and we have defined uj bar and uj prime. The following decomposition is valid. Uj instantaneous, function of space and time, equal to uj average, function of space, plus uj prime, function of space and time. The averaged values, then uj bar is limit t tends to infinity 1 by t time period, 0 to t is the time window, instantaneous u dt. This integral will be divided by 1 by t. And for fluctuations, uj prime over bar, which is basically again integral of uj prime dt divided by 1 by t, this is 0. Every instant it is there, but when it is averaged over the time window, it is 0. Now the phenomena that need to be described are sketched below. In a flow field, as I have already mentioned about it, that in some flows disturbances come from somewhere, maybe some external vibration, maybe roughness of surfaces, and then it grows. So one can see infinitesimal small fluctuations, those are growing, and now you can see fully developed turbulence. So this, how does it grow? This is very difficult to analyze. As I was mentioning, that in order to capture this transition, very powerful techniques like direct numerical simulation should be used. But for the engineering purpose, when turbulent flow may be called as fully developed turbulent flow, or fully developed turbulence is the state, then we can apply the statistical models that we have started discussing. Here I will give you another example. Maybe if you look at a velocity profile close to the wall, maybe this is a channel flow close to the bottom wall, maybe flow over a flat plate again close to the bottom wall. The computation of instantaneous velocity fields usually not attempted. Again, I have repeated, DNS is required for that, because too much information results for the entire flow field, that is for the variations in space and time. So this, at every instant it is varying. So if you take maybe 10,000 such instantaneous value and average it, then only you will get correct average. Usually, as again let me repeat, for engineering calculation, like we know for laminar flow, this is the variation. Similarly, for turbulent flow, some log law variation we know, and we'll get some such variation. So if we apply DNS, we will get all instantaneous profiles. From there we have to get the time average profile. But we would like to go for a technique. We are aiming to sort of apply some technique so that directly we can get this log law profile obeying the basic physics involved in creating such profile. So the continuity equation for constant density flows, we can write del ui del xi equal to 0, and this ui is instantaneous, so this is del xi of ui bar plus ui prime time average plus instantaneous equal to 0. The time average of this equation yields that del xi of this over a time window should be equal to 0. And if we write it in this way, time t tends to infinity, 1 by t, this time window, the integration over this time, ui bar plus ui prime, then we will get obviously the continuity equation satisfied by time mean quantities. And if that is true, then again substituting in this, we will get that the continuity equation is satisfied by the fluctuating components also. So if we say u, v, w, three directions, u del u del x del u bar by del x del v bar by del y plus del w bar by del z equal to 0. Here del u prime by del x plus del v prime by del y plus del w prime by del z equal to 0. So continuity equation is satisfied by the time average quantities. Continuity equation is also satisfied by the instantaneous fluctuating velocity component. At every point in time, the turbulent fluctuations have fulfilled equation 4 exactly. Now, let us discuss some laws of averaging. Let A be some A hat be some instantaneous quantity which can be expressed as A bar plus small a prime, and B hat is B bar plus small b prime. This is average, this is fluctuation, this is average, this is fluctuation. Averaging yields per definition 1 by t 0 to capital T a hat dt equal to a bar. Similarly, 1 by t integration 0 to t b hat dt is b bar. So that means a hat bar is a bar, b hat bar is b bar, which means a prime bar is 0 and b prime bar is 0. So time average of fluctuations is 0. Time average of b fluctuations is also 0. Then if we take two quantities a hat and b hat and perform the averaging of that, we can write a bar plus a prime, b bar plus b prime over bar equal to a bar b bar over bar plus a prime b bar over bar plus b prime a bar over bar plus a prime b prime over bar. Now a prime b bar over bar and b prime a bar over bar, these quantities are 0, and so because we have already mentioned about a bar over bar is 0, b bar over bar is 0, so that will make these two quantities 0. So a hat b hat over bar we can write as a bar b bar over bar plus a prime b prime over bar, which will give us a bar into b bar plus a prime b prime over bar. So a prime over bar is 0, b prime over bar is 0, but a prime into b prime over bar is non-zero. Okay, so and here we have a prime b bar over bar is a prime over bar into b bar, and a prime over bar 0, so this quantity is 0. Similarly, b prime a bar over bar, this operation will give us b prime bar into a bar, b prime bar is 0, so this is 0. So that is how this quantity will be 0, this quantity will be 0, but this quantity is non-zero, and this quantity will produce a bar into v bar. So this is what is usually called also Reynolds decomposition, and we can apply this to momentum equation. So the intention notation, this is usual momentum equation rather momentum equations, because we are writing uj hat, which will represent three velocity quantities in three directions, and ui hat. So basically this is temporal term, convection term, minus dp hat del p hat del xj plus del xi of tau ij hat plus rho gj. If one adds continuity equation multiplied with uj hat, we can get this. And this is basically allows us to write the momentum equation in conservative form. So this we have done earlier, but here we are using the tensor notation and doing that. So this is plugging in continuity equation, means we are basically writing momentum equation in conservative form. Again, uj hat is uj bar plus uj prime, and ui hat is ui bar plus ui prime. If we introduce that and perform the overbar operation, we will get del xi into rho ui bar uj bar plus tau ij bar plus u I prime uj prime over bar equal to minus del p bar del xj plus rho gj. So basically we write conservative form, then we substitute basically instantaneous quantities as mean and fluctuations, instantaneous quantities as mean and fluctuations. Then we do this substitution and apply overbar, and this equation will result in. The individual steps to derive average momentum equations, as I said, that what we did is 1 by t 0 to t del xi rho ui bar plus ui prime uj bar plus uj prime dt, and then we have written, expanded this ui bar into a uj bar plus ui prime into uj bar plus uj prime into ui bar plus ui prime into uj prime, and this after overbar operation, this term will be there, this term will be there, these two terms will not be there. So we will get del xi rho ui bar into uj bar plus rho ui prime into uj prime over bar equal to minus del xj of p bar minus del xi of tau ij bar plus rho gj, where rho ui bar uj bar is the convective momentum transport, rho ui prime uj prime over bar is the turbulence caused momentum transport, and tau ij bar is molecular momentum transport. This is basically shear stress arising out of molecular viscosity. So if we want to write this equation as specially u or x direction momentum equation, this term is 0 here, time average term for del t, we can if u bar is 0, we can call, this rho del t of u bar, for steady flows in a time average sense, steady flow, it can be made 0, which has been done here. But while writing this, I have separately x direction momentum equation, I have written that then rho u del u bar del x, v bar del u bar del y, w bar del u bar del z equal to minus del x of p bar plus mu del square u bar. And here we have written minus rho. That means we transfer the center quantity from left to right. And then we can write minus rho del x of u prime square bar del y of u bar v bar u prime v prime over bar, sorry, del x of u prime square over bar del y of u prime v prime over bar and del z of u prime w prime over bar. And we have already said that u prime bar is 0, v prime bar is 0, w prime bar is 0, but quadratic quantities u prime square bar, u prime v prime bar and u prime w prime bar, those are non-zero. So above equation, here this equation looks like laminar flow equation, with the exception that the velocities are average velocities and there are additional stresses arising out of the fluctuating components. So if you consider our x direction momentum equation for laminar flows, this term is there. Only thing, we are writing u as u bar. All these terms are there. Only thing here, u and v we are writing as average quantities. This term is also there. Difference is p we are writing as p bar. And this term is also there, mu grad square u. Here u is u bar. So this part is just like laminar flow equation. The velocity and pressure quantities are replaced by time average quantities. This is additional term, and this additional term is generated because of fluctuating components, activities of the fluctuating components, and this behaves as additional stress in the flow field. So when we will get corresponding terms for y momentum equation and z momentum equation, then these 3, again 3, again 3, those 9 terms will behave as a stress tensor. Exactly, that's what we have written. Sigma t is then, here we have written del x of u prime square bar del y of u prime v prime over bar del z of u prime w prime over bar. So basically gradients of them will be appearing in the equation, but we can write them as this fluctuating components: u prime square bar, u prime v prime bar, u prime w prime bar. Similarly, contribution for from y momentum equation will be u prime v prime bar, v prime square bar, v prime w prime bar, and z direction momentum equation will be u prime w prime bar, v prime w prime bar, and w prime square bar. So sigma t is the Reynolds stress tensor, written in compact form as minus rho u I prime u j prime over bar. And obviously when we get them in the momentum equation, gradients of them appear, just like molecular stress, the usual shear stress and the normal stress. Here also we'll get the contribution of this stress tensor in the momentum equation. So now sigma xx we can write as new sigma xx, which includes both this molecular viscosity and that velocity gradient will include this. Similarly, shear stress will include contribution of fluctuating components. So the quantities rho u I prime u j prime are the turbulence caused momentum transport terms, and if we use the tensor notation, we can write rho u I prime u j prime over bar equal to all these quantities. We have already mentioned it earlier that rho u1 prime into u1 prime bar, rho u1 prime into u2 prime bar, rho u1 prime into u3 prime over bar. Like that, we get other 6 components. This tensor is symmetric and has 6 unknowns. Basically, if we really look into this is unknown, 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 this is unknown. So since it is symmetric, we need not count these 3, but 1, 2, 3, 4, 5, 6 unknowns. And this is analogous to Ti j bar, which is coming out of molecular viscosity. So we can say that this stress, additional stress, which is coming out of fluctuating components, just following the usual stress components, we can model it as mu t. Instead of molecular viscosity, this is turbulent viscosity, into again these average quantities, which is del xi of uj bar plus del xj of ui bar plus 2/3 k delta ij. This is Kronecker delta. I will specially discuss why this has been added. But here, if we accept adding this term, as I said, we'll specifically discuss about it, but keeping that aside, there is striking similarity between these two. Only the molecular viscosity is substituted by eddy viscosity, and again this is a basic property, and this is not a basic property. This is created because of the interaction of the fluctuating components of turbulence. And now I will discuss that part, that why we wrote 2/3 k delta ij. So minus ui bar minus ui prime uj prime over bar, sorry, minus ui prime uj prime over bar is written as nu t. So this is same as what we wrote here, only we are transferring rho on right hand side. So having done that, we can write that nu t into del xj of u I bar plus del xi of u j bar plus 2/3 k delta ij. The term involving Kronecker delta ij is perhaps a somewhat unfamiliar addition to the eddy viscosity expression. It is necessary to make the expression applicable also to normal stresses when I equal to j. So why did we add this? In order to explain that, let us say, when let us substitute I equal to j, then we can write u1 prime square bar equal to twice nu t del u1 over bar del x1 plus then u2 I equal to j. So another will be u2 prime square bar. Then this will be minus 2 nu t into del x2 of u2 bar, and this is, sorry, this should be u3 square bar, and this one should be substituted by 3. I'm sorry, this is a mistake. This u3 prime square bar, like u2 prime square bar, u1 prime square bar, this will be u3 prime square bar equal to minus twice nu t del x3 of u bar or u3 bar. So now because if we do not have this, only the first part we are writing, let us imagine this was not there, this is not there, then we will get this. And then if we add it up, it is basically del u del x plus del v del y plus del w del z, continuity equation. So sum is 0 because of the continuity equation. However, all normal stresses are by definition positive quantities, and their sum is twice the kinetic energy k of the fluctuating motion, where k is given by half u1 prime square bar, u2 prime square bar, u3 prime square bar. This is the turbulent kinetic energy. So kinetic energy of the fluctuating motion we are supposed to get when we add all normal stresses. But if we add all normal stresses here, we will get continuity equation equal to 0. And this incoherence is coming, and in order to remove that, we are adding minus 2/3 k Kronecker delta. inclusion of the second part of the eddy viscosity expression assures that the sum of the normal stresses is twice K. Now it is assured this is twice K. The normal stresses act like pressure forces that is perpendicular to the faces of a control volume. And because like the pressure itself, the energy K is a scalar quantity, the second part contributes to modified pressure. So now it is consistent. It produces, of course, with all normal stresses 2/3 K, 2/3 K, 2/3 K. That 2/3 K can be absorbed in the pressure, and then everything is consistent. So now what we are going to do, we have basically continuity equation, and this is del xi of ui bar in all time averaged velocity components, and we have basically the momentum equations in three directions. And in the momentum equations we have this additional stress term, which is ui prime uj prime over bar, and as I said, gradient of that will come in the momentum equation del xi. So this, if we look into it, I have already mentioned that there are 6 unknowns. u1 prime bar square over bar, u1 prime bar, u2 prime bar over bar, u1 prime bar, u3 prime bar over bar, then u2 prime bar, u3 prime bar over bar, and u2 prime, u2 prime, that means u2 prime square bar, and u3 prime square bar. So these 6 components means u1 prime square bar, u1 prime into u2 prime over bar, u1 prime into u3 prime over bar, u2 prime into u3 prime over bar, u2 prime square over bar, and u3 prime square over bar. These quantities will again just go back for readily remembering it, like this quantity, this quantity, this quantity, this quantity, this quantity, this quantity, or as I have already mentioned, this quantity, this quantity, this quantity, this 1 2 3 4 5 6. So these 6 unknowns are there, plus u3, components in 3 directions, u average components and p average. So 10 unknowns, but available equations are 4. So there is a problem, it is called closure problem. Equation 8 and 9 are referred to as Reynolds equations. One sees that correlation of the velocity fluctuations ui prime uj prime over bar yield a new term in this equation. This term is usually referred to as Reynolds shear stresses. It represents the momentum transport caused by the turbulence fluctuation. This tensor contains 6 independent components. Additional equations are needed to solve these problems. But just I am proposing something, that what we have done here, if we can write this ui prime uj prime over bar as mu T, which is turbulent viscosity, into del xi uj over bar plus del xj ui over bar, then in this equation again this ui prime into uj prime over bar will be expressed in terms of u I bar, u j bar and their gradients. So basically then again we will get 4 equations and 4 unknowns in terms of velocity and pressure. But when we will do that, we will get one term which is basically mu t or nu t. This mu t or nu t is not known. This nu, which is molecular viscosity, is known fluid property. But when we will express this in terms of the velocity gradients, that means shear stresses, we will get nu t. So in terms of number of equations and number of unknowns, again we will have a balance, but nu t is not known. So entire challenge will be to find out nu t. It is not a fluid property, so it is not known a priori. It is a function of the interaction of fluctuating components. So depending on turbulent fluctuations and in the field, whatever is the turbulent kinetic energy and their dissipation rate, this will be controlled or the nu t will be determined. So in the next lecture we will discuss that aspect thoroughly. Today we'll stop here. Thank you very much. Thank you for your interest. Thank you.